I'm not Andrea Valle, but a substring of my name matches a substring of his name, so I think it's just fine. And I welcome and actually encourage the presenter to sit in the front so we can minimize latency, as we have discovered it's quite important. Never touch the HDMI cable. The computer has a missing keycaps. Don't stare at it. It feels your fear. So let's start with the first presentation here. That will be Delia, a noise-based virtual synthesizer presented by Cecilia Rossi, Giorgio Presti, and Federico Vanzini.
Com'è che si fa Ctrl N?
Ctrl Shift F to maximize.
So view full screen mode.
Okay. Okay, so it's left right. Is it on? Okay. Hello everybody. We are Cecilia Rossi, Giorgio Presti, and together with our beloved Federico Vanzini, we are presenting Delia, a noise-based virtual synthesizer. First of all, a little bit of context. We enjoy noise as a manifestation of truth. And we wanted to explore the possibility of using noise to create sound. And in particular, this instance is based on the conjunction between noise and bit crashing, so digital degradation of the signal. What we did is a virtual synthesizer where pitched and non-pitched sounds arise from noise only. So noise is the main source of audio material from which we extract all other sounds. It is supposed to create intentionally low quality texture and to be used in sound design scenarios, but also to create some original element in pop songs and stuff like that. Of course, the idea of using noise in a synthesizer is absolutely not new at all, but we wanted to put the noise in the center as the protagonist of the synthesizer, because we believe that new design strategies will lead to new ideas that a musician can explore. This is the main architecture of the whole synthesizer, and the black boxes are the oscillators, mixer, and other sound modifying boxes. And all the dashed ones are basically control signal. So from the keyboard, from LFOs, EGs. As you can see, is the typical subtractive synthesizer architecture with normalized patches. What is original actually in our synthesizer are the oscillators. And Cecilia will talk to you about the oscillators.
As you can see in the slide, this is the oscillator architecture. We have different stages, starting from white noise. The first one is generator, which performs a resistor capacitor filtering, starting from the note that is played by the user on the keyboard. Then we have a degradation stage, which performs resampling and requantization. Then we have a filtering stage, which performs a narrowband frequency filtering. And at the end, we have a saturation stage. As you can see in the slides, as it is depicted in the graphic, saturation can be done in two different ways, adding odd harmonics only, or both odd and even harmonics. In this slide, you can see the effects on the signal. Starting from generator, we have colored noise. Then we move to degradation, and it is possible to notice that we have a structure in the signal, a pattern. Then we move to the filtering stage. And at the end, we have saturation, which adds harmonics, as we described in the last slide. This is our GUI, the Daily Noise Synthesizer GUI, and feel free to scan the QR code. Okay, we will listen to some samples from the synthesizer. We have single oscillator samples or two oscillator samples. Okay.
So we will let you now hear some pseudo-sinusoidal signal made by filtering noise. As you can hear, is sounds like a filtered noise, as we expect, basically. But with the wave shaper we talked about before, thank you, Cecilia. Wave shaper we talked about before, we can add also odd harmonics, or even harmonics. What we are hearing is basically just one oscillator with no additional filtering, modulation, and stuff like that. As you can hear, is they remind somehow the basic waveforms of synthesizer, but they are more noisy, more wrong, basically. We love errors. There are a lot of other samples that you can hear at the poster or at this link. The QR code is also at the link. And that's it. So, see ya at the poster.
Thank you. Next we have Ciaramella, a synchronous data flow programming language for audio DSP. Paolo Marrone, Stefano D'Angelo, Federico Fontana, Gennaro Costagliola e Gabriele Puppis.
Okay, hello. I am Paolo Marrone. I'm presenting you Ciaramella, our new synchronous data flow programming language for audio DSP. And yes, we really needed another one. So, oh, bad. Okay. Okay, better. So it is actually based on a new approach that is a combination of the synchronous data flow computational model that is known for its scheduling, static scheduling property, and it is based on a full declarative syntax, so you can use variables before they are actually declared. This combination leads to a natural representation of the DSP algorithm, a high level of modularity and composability. Okay. It is actually very simple, and it's based on a few concepts, like the block, which is the encapsulation of an operation, and it can be atomic if the operation is simple, like the arithmetic ones, or the one sample delay. It can be also composite if it is made of other blocks. So blocks can have ports, input and output ports, and they are attached to each other via connection, of course. So to show you the syntax of Ciaramella, we implemented a wave digital filter. This is a simple low-pass filter of one pole, I think. And yes, wave digital filters are known to be hard to code DSP systems. So you can see that you can declare global constants. You can declare composite blocks, MATLAB fashion with the inputs and outputs. And you can actually use them by instantiating them if you want to use our terminology. And well, the important thing to know here is that the compiler does not add any delay at any point when creating connection or loops. So the user is required to add a delay at some point of the loop. In this example, the delay is set within the capacitor. So Ciaramella code is then fed to our compiler that, of course, is called Zamponia, and it has some intermediate phase. There is an intermediate graph representation that gets flattened and then static scheduled. So on the left, you can see the this intermediate graph before the flattening operation. And you can see that the instantiated composite blocks are seen like black boxes. So theoretically, this system is uncomputable because there are not delays outside these instances. So the flattening operation is the substitution of the composite blocks with their inner blocks. So you can have a final graph with only atomic blocks. This reveals the presence of eventual delays, and this makes the system computable. Finally, the system gets scheduled, and that's just the search of a proper order of blocks that is computable. And this is what we call modularity and reusability of the code. Thank you.
Okay, the next presentation will be Count Me In, a collaborative step sequencer for audience participation by Juan Pablo Carrascal.
Thanks very much. Yes, my name is Juan Pablo, or JP Carrascal. I am a UX researcher at Microsoft, but this presentation doesn't have anything to do with my work there. I'm going to present Count Me In, a collaborative step sequencer for audience participation. A little bit about the motivation of this project. Throughout human history, music has been an activity that promotes social cohesion, and traditionally, music events were very participatory, with people taking an active role. Actually, the separation or differentiation between participants and audience, participants being the actual performers, is one that is predominant in modern Western music, but it was not so common in the past. With the project that I am presenting today, what I want to do is to explore the modern web technologies to create an experience that returns to the social origins of music making. So the design rationale of Count Me In is to adhere to these principles. I wanted it to be collaborative by making participants conscious members of the music making activity. I want it to be social, but also hopefully fun as well, as it should promote social interaction as opposed to be focused exclusively in individuals' contribution. I want it to be interactive by providing a clear sense of agency to the participants of the activity. I want it to be democratic by making it easy for everybody to participate without any complex software installation or authentication. And finally, I want it to be scalable. It can be used for different activity types and sizes, from social gaming, but also in other larger events combined with other musical instruments. Sorry for a bit about Photoshop there at the right. Count Me In is composed of 3 applications. So far, it's still in development, but so far, there's a sequencer that is meant to be seen by all the participants. It renders all the audio. It uses the web audio API, actually. There's also a drum track, and you will probably recognize that this is all based on step sequencers like those in drum machines. The drum track is a single drum track from a step sequencer where you can control the steps. You can turn on and off individual steps. And you can also adjust the volume of each note of the sequencer. And then with the synth track, you can create melodies with this kind of keyboard-like interface per step. The sequencer is meant to be visible for all the participants of the activity, and you can recognize your contribution in the interface. But the drum track and the synth track are going to be run on each individual participant's device. The architecture of the device, a little bit on that, it's based on a Node.js backend. It's running on a web server or cloud server. The track applications run on, as I mentioned before, on individual participants' devices, but the sequencer should be run on a computer that should be amplified, and maybe its video should be projected so everybody can see it. I am currently working on synchronization between the sequencer and external software and hardware using the MIDI API, the Web MIDI API. So it would become easier to synchronize with other systems and also to connect synthesizers, hardware synthesizers, digital audio workstations, and so on. In the paper, if you read it later on, there's a description of a very, very simple, small preliminary study. So no scientific rigor there, but it kind of helped me to find ways to improve the interface in the future. But it actually engaged, I found that it engaged participants, and it was very interesting because they started focusing on the individual contribution to the composition, but then they switched to more kind of collaborative strategies, paying attention to what other participants were doing, and there was a very playful dialogue between participants. So I think to that degree, to that effect, it meets the expectations. Thank you very much. This is all. The project is live. You can start by visiting the website, and see you later in the poster session and also in the demo session later today. Thank you very much.
Thank you. The next presentation will be Designing the Balance Between Sound and Touch, Methods for Multimodal Composition by Claire Richards, Roland Cahen, and Nicola Misdari.
Thank you. Hello, everyone. My name is Claire Richards. I will be talking to you today about a part of my PhD research through an article titled Designing the Balance Between Sound and Touch, Methods for Multimodal Composition. So, the main motivation behind this research actually comes from something quite personal. It comes from my own hearing disability. And so what I want to do through my research is to enable users with any hearing profile to appreciate a body-centered listening experience. So to broaden this inspiration so that anybody can be included, no matter your hearing. By simultaneously exciting the senses of touch and hearing by placing vibrations in direct contact with the body. So therefore, we developed a wearable audio tactile device and designed multi-sensory effects for the body. So what is this device? It is something I call the Multi-Modal Harness. It's something that I developed over the course of about 1.5 years in collaboration with a costume design studio and with my research partner, Actonica. And it contains 9 voice coil motors and a 20-channel audio haptic card that allows me to control each of these actuators independently. So I need to give some context about why we made this, because that's the whole purpose behind this research. I'm interested in something called extra-tympanic sound conduction. Many of you may know this as bone conduction. I call it extra-tympanic because it involves everything that doesn't involve your eardrums. So muscles, ligaments are also involved. And it doesn't just talk about your skull. Also structures of the body that I've studied, such as the spinal column and the clavicles, are also capable of transmitting vibrations up to the inner ear and producing percepts of sound. So what's interesting is that when you use bone conduction, or ETC as I call it, you also have the sense of touch that's stimulated within a certain range of frequencies. And I'm interested in this certain range of frequencies that overlap auditory and tactile sensitivity that we see below there. So to be able to explore the capacity of this device, we needed to design some interfaces, because otherwise, how do we know what the body is capable of perceiving in terms of more aesthetic experiences? So we conducted a collaborative workshop last year, exploring 3 themes of sensory composition, which are multimodal music listening experiences, spatialization of audio-tactile signals on the body, and sensory equalization, or more the calibration of the vibrations to individual sensitivity and to the different sensitivities of each point on the body, because they differ. So the first interface is called mono point-to-point, or the body spatialization interface, where essentially we're choosing a one-dimensional configuration. We see 3 options on the left here, where the signal is routed across different groups of channels. So we can create trajectories across these different configurations that allow us to create patterns of spatialization. So we can set the waveform, modify the position, the amount of time that the signal spends at each position, the frequency and the amplitude across the short duration of the composition. The second is inner music. It's a multimodal music player. It's quite basic. Essentially what we have is the playlist object. A high shelf filter attenuates the bass frequencies because we perceive those so much better via tactile. And then each position on the harness has an equalizer so that we can basically balance the different frequencies, amplitudes, and change the focus between audio, tactile, or bimodal perception. And then finally, there's drummer. It's the body-based drum machine and step sequencer. So for here, we have different files associated with each position on the harness. And you can import and select any sound files you wish, and create patterns of stimulation by activating the different buttons on the sequencer and changing the other parameters in the interface. So in conclusion, what we learned is, what's interesting is spatial audio information is lost when we're perceiving things through extra tympanic conduction, because everything, even if we think we're hearing something on the clavicle, everything is being routed up to your neck, to your inner ears. But the tactile sensation gives you the impression of an auditory source location. Attention and expectations regarding the auditory of the experience of the device might also impact users' judgments, because they're expecting something that sounds like something that they know, that has been designed for their ears, and that's not what this is about. And additionally, morphological differences have a very strong impact on signal perception and body movements, the way that we stretch our skin and our body. In future work, we're going to continue the studies of sensitivity and then incorporate this data into the future iterations, which will be consolidated for longer length compositions. Thank you very much.
The next presentation will be Analysis and Evaluation of Visual Cues in Graphical Interpolators from Darrell Gibson and Richard Polferman.
Hello everyone, my name's Darrell Gibson. I'm from Bournemouth University, and this is a collaborative project between Bournemouth University and University of Southampton. Little introduction. I'm sure most of you are familiar with what a graphical interpolator is, but just for those of you that aren't, graphical interpolator allows you to interpolate between presets of parameter values. This one is the one that comes in MaxMSP, affectionately known as nodes. It uses an intersecting visual model. So each preset is represented by a circle inside the interpolation space, and you can then move the cursor, and when it's in an intersecting region, it will then interpolate between the parameter values. My particular area of interest is using these systems to control synthesis engines as a mechanism for sound design, to provide a level of abstraction between the user and the low-level synthesis parameters, which sometimes can be in the region of hundreds of individual parameters. Over the years, a number of different visual models have been created, and I've just got 6 examples here that all use a different visual representation. Now, an earlier study that we undertook showed that the more visual cues the interface presents, the greater the perceived usability of the system tends to be. So what we wanted to do was examine a variety of different interpolators, all that provided different visual cues to the user, to see if we could come up with some understanding of the perceived usability and performance of these systems. The first thing that we did is came up with a dimension space analysis to understand, try and get a better understanding of the visual cues that the different interpolator models actually present to the user. We came up with a 6-axis dimension space, and we designed this in such a way that visual cues were on the individual dimensions. Anything that was constant with all of the interpolators was left out because there was no point. We wanted to understand the differences between the interpolators. And we took an assumption on the perceived desirability of each of those. And so we positioned the axes with increasing desirability of those cues as it works out from the origin. For the 6 interpolators that I've just shown you, these are the dimension space analysis that we did. So those that are converging around the origin of the dimension space could be perceived as being less desirable to those that have a very wide spread of the visual cues. To verify this, we then undertook user testing to see if there was a correlation between the dimension space analysis that we did and the actual usability of these. So we designed a interpolator usability experiment where we asked users to come in and use all 6 of the visual models for a sound design based task. Each of the models was populated with identical preset sounds at identical locations within inside the space, and users were then asked to design a background ambient sound for a science fiction based spacecraft. We then captured all of the users' interactions with the interpolation space. So we captured all of their mouse movements. Here you can see I've plotted these back onto the original interfaces so that we can view the searches or the journeys that the users made through each of the interpolation spaces. From this, we could then do statistical analysis. So we then undertook statistical analysis to try and evaluate the user's performance. I won't go into details here, but if you'd like to know more of the details and our conclusions, please come and see me on the poster stand. Thank you.
Okay, our next presentation would be the Teinophone by Leo Fogadic and Dan Overold.
Okay, hi everyone. My name is Leo. I'm a student of the Sound and Music Computing Master's Program at Aalborg University in Copenhagen. And together with my professor Dan Overholt, I'm going to present you the Teinophone. So the Teinophone is an electronic string instrument enabling unconventional and alternative playing techniques. So when we're thinking about the interaction design of the instrument, we had a couple of things in mind. First one being that it has to include signature features. So features that are exclusive to that device. But we also wanted to offer familiarity with more conventional instruments. But with string instruments, traditional string instruments, their strings are stationary by necessity. So they only move, they only vibrate and resonate due to excitation. So we wanted to incorporate extended movement of strings to produce a variety of sounds and timbres. So the interface looks like this. It's 7 strings laid horizontally and parallel to one another. And while thinking about the interface, we set a few goals. So in order for the instrument to be used by anybody, regardless of musical experience, the first goal is transparency. So the player should realize quickly how to use the instrument and how to play it. Also, the second goal is precision. So the input data and processing of the data should be as precise as possible to enable the player to have as much control as possible. We also, the third goal is expressiveness. So we wanted to accompany players' virtuosity. So to be able for the player to convey their virtuosity through the instrument. So how you interact with the instrument, there's 2 types of interactions. The first one is plucking the instrument, the strings, which produces a sound made by the Karl-Press-Strong synthesis method. And the other interaction is pulling the strings or drawing the strings out of the instrument's body. And that controls a physical model of a bowed string made in Faust. So when you plug the strings, there's a parameter that's velocity. So how hard you plug the string controls the velocity, and the bow string has parameters like velocity, pressure, position, and vibrato. So the strings, they're actually, it's just a rope. It's not elastic as it might seem. So this is, these are the inner components of the instrument. So there's this 3D printed housing, and it houses a potentiometer that's on the bottom, and it's actually a 10-turn potentiometer. And when you close this encapsulation, there's a metal coil, like a spiral spring, that creates a tension, and that it enables the string to, when it's pulled out, to retract back inside in this contraption. So this is the representation of the inner components of the instrument. So there are 14 of these contraptions, and they are all connected to a Teensy microcontroller, which has the audio adapter board mounted on it. So this project is still a work in progress, and there's a lot of improvements for it. What would we like to do more about it is to incorporate more sounds, so different, greater variety of sounds and timbres, and also to morph between the sounds when you pull the strings. So the strings can actually be pulled out about 1 meter high, so there's a lot of range to morph between the sounds. It would also be useful to tune the strings, so the player can tune the strings by themselves. Now it's only tuned to a minor scale. Also, pitch bending would be useful for expressiveness, and we could also add different sensors, like ultrasonic sensors, to enable hand movements to control different audio effects or sound manipulations, and of course, just refinement of the algorithm and yeah, just general improvements. So if you want to hear how it sounds, if you want to try it out, please come to my poster, and yeah, thanks for your attention.
Okay, our next presentation will be a new sensor technology for the sonification of proximity and touch in closed-loop auditor interaction by Pascal Stout, Anton Kogge, Marcello Lussana, Marta Rizzonelli, Benjamin Stahl, and Jin-Yang Kim.
Hi, My name is Pascal, and I will present a new sensor technology for the sonification of proximity and touch in closed-loop auditory interaction. In other words, we developed a new wireless sensor that can detect proximity and touch between two persons and sonify it in real time. But why would you want to do this? In many art performances with the early version of the system, we experienced that sonifying interbody proximity causes strong reactions. So many participants reported after the performances an increased body awareness or a felt connection to the other participant. And so it didn't take long that we got attention of several music therapists and started collaborating with them. And after some quite boring paperwork, the art project Saint-Étienne became a research project at the Humboldt University in Berlin. And we are combining human-computer interaction, sonic interaction design, and real-world research to investigate the relationship between sound, sociality, and therapy. And one of the main goals of the project was to develop a wireless version of the system. But why wouldn't we just use established systems, such as infrared or ultrasonic, for the proximity detection? The problem with these systems is that they rely on a clear field of vision because they measure proximity at discrete points. So they are not very convenient for musical dyadic interaction, which needs freedom of movement. Before I explain shortly how we overcame these limitations, I want to show a demonstration video of our system. So probably you're wondering now, how does this work? To keep it short, our system is based on capacitive coupling between the two bodies. The closer the bodies are, the stronger the coupling, and we exploit this proximity effect to derive an interbody proximity signal that we mapped on algorithmic sound environment in real time. If you want to know about the technical details, I invite you to read the paper or come to the booth. What were the main challenges? First, developing a new wearable sensor technology required many prototype iterations and a lot of hardware hacking and soldering, and yeah, this was quite challenging in the small team that we had. Second, the weak ground coupling compared to the wired version of the system. We overcame this by developing custom conductive shoe ground electrodes that are attached to the shoes. And last but not least, organizing interaction studies during a global pandemic. To sum it up, based on capacitive coupling, Saint-Étienne overcomes the limitations of established systems for interbody distance detections. We can measure proximity up to approximately 4 meters, and our prototypes were successfully used in couple therapy sessions. Thank you, and see you at the booth.
our next presentation will be the Spatbox, an intuitive trajectory engine to spatialize sound by Pierre Lecomte.
Hello. Should I close this one? Folder, presentation. It's double click here. Okay. Okay. View. Presentation. Full screen mode. All right. All right. Hello, everyone. I'm Pierre Lecomte. I'm an associate professor at University Lyon 1, next city. And today I'm going to present you the Spatbox project that I've been working for a few months now. It's on spatial audio. In my view, for the background, like we have spatial audio everywhere nowadays, like in music, cinema, concerts, gaming, virtual reality, even at SMC-22 for some concerts. There is an important software offer to create immersive sound content around. But, however, I've been asking myself, like, artists often need to access a special venue or equipped studio with many loudspeakers to create immersive sound content. And the question I've been asking is, what about an autonomous, like all-in-one simple interface for live performance to spatialize sounds with a few loudspeakers for an ordinary musicians? Like my target would be the guitar player, the teenager in his room. You want to play the guitar, you buy a guitar, you go and you play it. Is it possible to do the same with the spatial audio? So the idea of this tool would be to input directly analog signals. You plug your synth, your guitar in it, and outputs directly the loudspeaker signals. Should be affordable and use a few loudspeakers that anyone can build this thing. And of course, I target live performance experimentation with that improvisation. So the approach I retain for that is to use FOSS that I've been working for many years now, and to target an embedded system such as Raspberry Pi, Bella, or Teensy, which comes now with multi-channel audio hats. For instance, Bella can go up to 16 outputs with the Beast version. And the spatial engine would be done with ambisonics. I can argue for that if you come in my poster. And it runs with ambitools, that toolbox that I've been developing for a few years now. Okay, so what about the trajectory, how to generate them? There is an infinite way of doing that. So I retain the parametric trajectory approach. So the idea is to generate a multitude of trajectories by turning a few knobs. And the user will generate new trajectories by changing the parameters of the equations. So you have to describe, in a way, each coordinates, like x, y, and z, over time, or in spherical coordinate system, radius, azimuth, and elevation. And the question is which coordinate functions to choose to assign to each parameter. So I've been retaining the LFOs from the synth world. So one LFO per coordinate. So, and by varying the waveform of the LFO, its amplitude, frequency, and phase, you can generate a trajectory patch. So I have so far in the tool like classic waveforms. And for instance, let's explain with an example. The red trajectory here is an helix. So you can start with a sine LFO on the x coordinates. So your sound's going to oscillate like that. If now you do the same with y coordinates, it's going to go diagonal. But now if you change the phase of the y with respect to x by a quarter period, you will have a cosine and no more a sine, so it's going to start to be a circle. And if you add on the z coordinate a sawtooth, you're going to have an helix. And so, on the right-hand side is the same example. In spherical coordinate system, you can describe flowers and whatever you want. So by tuning all the LFO parameters, you can create a trajectory patch. So you have extra features like choice of the coordinate system. Of course, we can activate or deactivate Doppler effect. You can scale and speed the trajectories by turning a knob. Alt and reset functions to hold the source in place and let it go when you release the button. You can have translation and rotation with respect to you, like if you want to move the trajectory or to turn it. And of course, you can compile the tool for any number of sources you want to spatialize. So I'm building an hardware prototype right now, so that, as you can see here with a Raspberry Pi, there is a Python layer around it to load and save presets. And I invite you to come and test the SPAT box at my poster booth. So thank you for your attention.
Thank you. Our next presentation will be a gaze-driven digital interface for musical expression based on real-time media physical modeling synthesis by Devanzo Kantpal, Prithvi Ravikantan, and Stefania Serafin. Familiar with LibreOffice? That should work. Nope. That shouldn't work. I did it. I really did. Export PDF. We're quickly going to solve this, don't worry. Yeah, the PDF was what was requested by the community, so I'm just sticking with what.
Thank you. Hi everyone, I'm Devansh on behalf of my group. We're from Aalborg University. Myself, Prithvi and Stefania, we worked on a gaze-driven digital interface for musical expression based on real-time physical modeling synthesis. So to start with, I'll introduce the work. It was motivated by the fact that individuals with severe physical limitations are often not included, and they miss out on conventional music making practices because it requires a lot of physical movement, be it the drums or the guitars or any other instruments. You need to move your feet, your hand, or even a combination of the both. So we do have DMIs or digital musical interfaces, but when we augment them with sophisticated sensors like eye trackers, and we use these modern fast computers that we have for real-time physical models, we can come up with a lot of interesting results and possibilities. But at the same time, eye-driven musical interfaces are still quite unexplored, and we believe that they present us with an exciting platform for sonic interaction, because we can use movement descriptors to map different eye movements to the music-making parameters of physical models, and this is what we've based our work on. So moving on, the aim of this project was to design a scalable and a robust prototype of an interaction that enables feasible gaze-based interaction for music, and it serves as a platform for exploring the potential of gaze-based interactions and hopefully takes the research forward. So I'll start with the eye tracking part of it. Now, when we say eye tracking, it often refers to gaze tracking, which means tracking the gaze of a user on a screen or something of that sort. Other applications do include eyebrow movements and eye movements and as such, but those are out of scope for this work, and they're often used in other applications like gaming or industrial or academic research. So the other parts of eye tracking that we have are blink detection. So we know when a user has blinked versus when they've not blinked, and the eye tracker does not react badly to it. So we have implemented an algorithm for blink detection. And the most important part would be defining saccades versus fixations. Now, saccades are basically non-lingering movements across the screen that essentially don't have to mean much, versus fixations are those moments when you can determine that the user has been fixating their gaze on a certain part of the screen. And how we did this was we implemented a fixation detection algorithm in real time using JUICE. And as you can see on the figure, it works on the fact that there is a saccade threshold, which is a radial distance from the current point, and any gaze points sampled within this radius are considered to be part of the same fixation. Those are the ones in red. And the ones in green are considered to be saccades because those are the points sampled that are away from that radial distance. Additionally, we also use the concept of dwell time to counter the Midas switch problem, which basically means that any artifact on the screen is only triggered after a few milliseconds of time, after which the user has fixated their gaze on it. On the hardware front, we tried the project with two eye trackers, being the Tobii X230 and the Tobii iX. They're quite similar. They sample at 40 Hertz, and the accompanying software was the Tobii Eye Tracker Manager for calibration with the screen and the Tobii K SDK in C. Now, we also use the weighted mean to calculate the current fixated point, and the equation below shows us that the most recent point has the highest weight in the weighted mean. That's all for the technical details on the eye tracking, but I'll be more than happy to talk about it and discuss it with the poster. Now, for the physical model, we used a damped ideal bar, and that's the equation of the physical model with the damping terms. Again, I'm happy to discuss the math at the poster session. We used a xylophone because it has a wide range of musical notes and has discrete musical keys. And the real-time implementation was done in JUICE, and the tuning was done by varying the length of the ideal bar, and the damping was adjusted by ear. So this is a graph showing the variance of the pitch of the ideal bar depending on the length, and the table shows the same. Again, I have more graphs and figures and also some demos at the poster session. This is the final iteration of the project, and the musical keys were organized in a circular manner, and that was inspired from the previous works that have been carried out in eye-tracked music. And we had some other control keys on the sides, and as you can see, that green square is the current gaze position of the user. I now have a small video demo which I think does not, oh, it does work. Although there is no sound for this, so again, I'll be, yeah. Okay, I'll just finish this up by going to the results. So the results was that we opened a scalable and open source prototype which has simplicity and intuitiveness, but also has certain challenges because of the difficulties with eye tracking and the lack of familiarity with it. And I invite you to the poster session to have a further talk about this, and we can also talk about the future works for the same. Thank you. Thank you for your attention.
Okay, our next presentation will be the Singing Shower, a melody-sensitive interface for physical interaction and efficient energy consumption. Jan Sesnek and Sandra Pauletto.
Left and right. Left and right. Yeah, yeah. Okay. Hello, hi. Yes, I'm Jan. Very nice to see you all. So I'm from KTH in Stockholm. I'm a PhD, first-year PhD student there, and together with my supervisor, Sandra Pauletto, we've made the Singing Shower. You're not supposed to laugh yet. I mean, you haven't even seen it yet. So this is part of the Sound for Energy project, which is about developing everyday sonic interactions to facilitate and promote energy efficiency, funded mainly by NRW Myndigheten, and there's our cool logo. So the Singing Shower is a shower where you sing to take a shower. When you sing a melody, it releases a flow of water. And as long as you continue singing, the water keeps flowing. So when you stop singing, the water stops. So this makes it quite similar to what's often referred to as a Navy shower, which is a traditional method for showering in places with limited resources. So melodic interaction as a form of control is relatively unexplored. Maybe because it's so vague. Singing, you know, I put little quotes on that, can mean a lot of different things to different people. So it can be a surprisingly difficult thing to define, and thus a surprisingly difficult thing to implement technically. So it did take a little bit of work, but we did make a prototype that worked. And it uses pure data to analyze audio input and a Bella controlling a water valve solenoid to actually control the flow of water. So you can actually see in this, the spectrograms were really fun to look at because you could really see the musical melody happening, then the giant burst of white noise, which is the shower. And then when the user stops singing, after it takes a second for the algorithm to kind of work out that the singing has stopped, and then the water stops. So yeah, it does work. It's entirely local. It's not like using machine learning or anything like that. It's just running a PD, very simple patch. So our paper describes the tests we did of the first prototype. I made a video. You can watch the video too of me actually taking a shower. You only see me from like the neck up, so don't worry. If you want the director's cut, you'll have to. But for the test, the user tests, we had to play it safe for the very first prototype. So we got them to control the flow of water by singing at a shower, which is a bit strange, but it did work for collecting data about how people felt about it. So singing in the shower is clearly and obviously like existing cultural phenomenon, as illustrated by the Google image search for singing in the shower. And so in a way, you can kind of see the interaction design of this as like a really good match, right? It piggybacks on existing interactions of singing in the shower, and it provides a distinct advantage of being able to control something that when your hands are soaping yourself, right? So you can control something without having to actually touch it. So it's kind of like a natural thing, right? It's a natural fit. But it's also totally absurd, right? And I think it's really difficult to justify it from a product standpoint, right? Like, who's going to buy this? But although I can tell you, as a user of this, it's surprisingly usable. Like, it's actually really a useful and fun thing to do. But I think that absurdity is actually a good thing, right? Because the interaction makes us think about what we're doing. It makes you think about why we're doing it, and also why there is that resistance to it. Why is there a resistance to this? There's a lot of resistance that we encountered in the test and the discussions and the research we've done about it. Part of it is about machine listening, which is problematic for many of us in this room. Like, people are scared of machine listening. That's really interesting because this was like a local thing. Why are people scared of this, and how do we get people to trust that we're not recording it and sending it to Amazon to be analyzed and sold? But then also, people really like taking luxurious showers. They don't want the shower to be turning on and off. And that's an even more problematic thing, right? Because a shower like this, research has shown that it can save about 50,000 liters of water per person per year to shower this way, right? But convincing people to do it, even with a fun kind of absurd, playful thing, is hard, right? So while I don't expect there to be wide adoption of the singing shower, I think it does provide a playful and provocative application of sonic interaction design that raises a number of questions about how we use resources and our sonic relationship to technology more generally. Obviously, I have a poster like everyone else, so come and say hi and talk about it. And yeah, that's the singing shower. So.
Thank you. I don't know if you also have a prototype here. That would be even more interesting. Our final presentation will be Design Concepts for Gaze-Based Accessible Digital Musical Instruments by Nicola Devanzo and Federico Vanzini.
Good afternoon to everyone. I am Nicola Devanzo from Laboratorio di Informatica Musicale in the University of Milan, and I'm presenting you this paper, which I wrote with my supervisor Federico Vanzini, which is part of a bigger work about accessible digital musical instruments. I'll talk about the main topics, and I'm sorry for there will be some overlapping with the work from Devansh and Pal, because I didn't expect. So basically, we are talking about musical interfaces which exploit gaze, or the 2D point where the musician is looking on a surface, like a screen or in space. Research on gaze-based musical interfaces has experienced a major boost during the few decades due to the availability of consumer eye tracker sensors at very affordable prices. These solutions are based on infrared cameras and are completely non-invasive, and they return a fairly noisy signal. But with that in mind, the development of interactive solutions is still possible. One of the main focus and target for our paper are motor disabilities. Traditional acoustical musical instruments are, in the vast majority of cases, require the use of hands to be played. There are musicians with disabilities like Mark Goffney, pictured here, which found a way through. But what if a musician has a quadriplegic disability and wants to play like a real-time instrument? Quadriplegic people are paralyzed from the shoulders down, and it means they cannot use their limbs to interact, neither fingers nor arms or feet. For them, interaction is possible using different physical interaction channels located in their head, such as breath, head rotation, and eyes, of course. And okay. In literature, there have been proposed different gaze-based accessible DMIs, and our papers aims at reviewing the main solution that these instruments have proposed. And in the image you can see Netitar, Lumiselo, the high harp, and I play the piano. Since eyes move very differently from fingers, the design requirements for gaze-based interfaces are very different. And the paper presents a review of the main ways in which eyes move, including saccades, fixation, smooth pursuit, and jitter. Some design cues and techniques used in the literature are then presented. This includes exploiting the color sensitivity of our peripheral vision in order to locate object positions without having to look at them, using certain types of pointers and cursors rather than others in order to avoid distraction and involuntary head movements, and using visual elements to enhance accuracy, and implementing automatic interface scrolling systems by exploiting smooth pursuits. But one of the main problems to be solved and taken into account is probably Midas touch. This seemingly sneaky but complex problem has to do with that inadvertent activation of gaze-sensitive interface elements. For example, in this keyboard, even if we do a very fast saccadic movement from the F key to the E key, the risk is to activate all the keys in between. And our paper summarizes several solutions for Midas touch proposed in the literature. And those include dwell time, the use of fixation discrimination filters, hybrid interaction with gaze, and for example, breath or head rotation, as well as different types of keys displacement that partially solve the problem, and which you can see in the lower side of this slide. So, thank you for your attention, and I'm looking forward to have a talk with you about this in front of a poster and to see and to show you a little demo.
Thank you to all the presenters of this session. We have a lot of very interesting to check, so please go outside and interact with our poster presentation. And we'll see at the next session, starts at 3:30, will be the first demo session. So here in 1 hour.